It's a linear representation of an actual more complex theory, which we have no idea about because we can't deal with crap like this, okay? Still, in this linear approximation, we have circles which are represented by neutrinos, electrons, and positrons, possibly other leptons as well, but we'll leave them for now. And we have simple baryons like proton, represented by the next not possible. So you can twirl a photon like this, you'll get neutrinos or electrons or positrons, or you can twirl it like this, then you'll get protons.
Greetings, this is Eugene the Philosopher, the greatest living philosopher after the unfortunate passing of Quentin Robert D. Nameland, who has been the greatest living philosopher before me. Now, in the comments under one of my previous videos, which was devoted to a quark model of hadrons, you have asked me to give you a better model, okay? A better model of hadrons than the quark model is, that is. So this is the video devoted to exactly that. I'm gonna show you what I consider to be a better model of hadrons than the quark model is, alright? So without further ado, let's roll.
Alright, let me start with a brief personal anecdote of a pretty sad sort, actually. So the author of this theory, Alexander Kyriakos, or Alexander Kyriakos if you wanna read it in I guess English type of transliteration. So he actually contacted me. So it wasn't me who learned about his theory. It was him learning about my blog in Russian in 2018. And he sent me a message via email, this letter, where he said that, well, I really liked your posts about, you know, dark matter and Stephen Hawking and things like that. So I replied to him, like he actually mentioned that he has a pet little theory, and I became interested. So I said, okay, send it to me. And he sent to me this book of his, which is, as you can see, 2006. Sadly, it's in Russian, okay? But luckily for you, it's, as you can see, it's 200 pages. Luckily for you, it's also available here in English. Even though it was translated by him, I read both Russian and English, so I can tell, you know, when somebody was translating from Russian, there are some figures of speech which are impossible to do in English, but you do it in Russian, and then you try to translate it as close as possible, and you acquire some artifacts sometimes, let's put it this way. So if you encounter something like this in this book, that's the reason, is that it was translated from Russian, essentially. But it's still... as you can see, it's almost 300 pages in this case, all right? So this is the book I'm gonna briefly talk about here that describes his theory of elementary particles. But still, let me finish with this anecdote because, as I've said, it's pretty sad. So as you can see, like, it happened in literally 2 days, our brief exchange. And then it took me like half a year to read this book, actually, and then I started like sending him letter after letter, okay, but he never replied. And my assumption is, well, he actually wrote in the very first letter, I think, like he said that he's pretty old. He's like 70 or maybe 80 years old, so like I can only assume the worst, sadly. So I never heard back from him, though I would really love to talk to him. So yeah, but it's all happened like 6 years ago anyway. So probably nothing happening right now. Unfortunately, again, that's one reason for you to talk to people more, you know. But I was busy, in my defense. I was busy with the conferences in 2019 that I've attended. There were at least 2. Okay, anyways, speaking about the theory, so I'll obviously link everything that I'm showing to you, so you can actually read it for yourself. It's free, the book is, that is, so you can look into it. It's very well written. Like, he actually says that he's also like a theoretical physicist. Like, he says his specialty is physics of nucleus and elementary particles, which is also my specialty. And this book is full of mathematics, unfortunately to some of you, but fortunately to some others, okay? It's full of quotes, it's full of references, it's really well researched in actually every respect, I might say. But even if you don't know the mathematics, I'll just recommend you to read it, okay? Because you can just skip the formulas and you can just read the text, because the text is clear enough, actually. And there are pictures. I'll show you some. Not all of them, but at least some, okay? So hopefully it will be illustrative enough. And as the author himself claimed, like his idea was to build a theory which would be the same mathematically as the current theory, but would make ontological, aka physical sense, you know, to basically bring back the ontology or physics into elementary particle physics, if you know what I mean. And this is kind of exactly what I talked about in my video about quarks, right? That we have this gauge invariance principle. I'll link the video as well in the description about the quark model. That we have this gauge invariance principle, which is kind of pointless. Like, I mean, it doesn't follow from anywhere, and yet everyone uses it and it seems to work. Well, why does it work is the question, right? And this is, well, at least partly, that was the reason for Kyriakos to develop his theory, all right? All right, so what is the theory? Let's take a look. So he actually uses 4 of the regular postulates of quantum mechanics, or quantum field theory, if you wish. So these are the first 4 postulates that Maxwell's equation for the field without sources. I mean, Maxwell's equations is basically his first postulate, is that these are the equations for the fields, all right? The second postulate, I mean, no one would argue with that. But then we have a quantization of electromagnetic waves, right? That the electromagnetic waves are the superposition of the elementary waves, wave fields rather, named photons, okay? Which all have certain energy and zero rest mass, that is. Again, regular stuff, postulate of dualism of photons. Photons are both waves. That's postulate number 3, so they're described by the wave equation. And they are also particles, according to Planck's formula, right? So this is all regular stuff. This is absolutely nothing new here. Nothing, like no new physics, no alternative theories yet. Here is where his theory comes in these 2 postulates. So the photon, according to Kyriakos, contains 1 wavelength, which corresponds to its energy according to Planck's formula, okay? So in Russian, the nouns have genders, so he wrote it like his, not its. So anyways, so a photon is exactly 1 wavelength. Now, he actually clarifies this, because if you ask a theoretical physicist, what is the physical meaning of photon's wave function, they'll have big problems, you see, because it's like basically like the usual treatment of the wave function according to Born's rule, for example, where it corresponds to the amplitude of probability of finding a particle in a certain spot, or in a certain state rather. It makes no sense for a photon. So a photon is inherently non-local. And it's a big problem actually still, you know, even after like it was recognized almost 100 years ago, and it's still a big problem. Actually, now the physicists are so retarded that they don't even recognize it anymore, at least the majority of them, okay? Or they don't care, like whatever you prefer. But it's still a problem, and that's how he solves this problem, is by postulating that a wave function of a photon essentially shows that a single photon is a single oscillation of a field, if you wish, a single sine wave, okay? I mean, limited, like from 0 to 2 pi phase, basically. But you'll see it later. So that's the first postulate, is that a photon actually is limited in size, all right? Back in the day, they used to call them Zugs, you know, the German word for a train, like a wave train. It's written as Z-U-G, Zug, the German word for train. So it's kind of like this elementary Zug, 1 photon, right? Like 1 piece of a sine wave. And then the second postulate is that the massive particles are formed by essentially twirling this single photon into a closed, well, Kyriakos calls this EM string. EM stands for electromagnetic, but I mean, whatever you want to call it. just some sort of a closed structure, okay? And that's how you get, according to Kyriakos, all the other particles. So let's take a look. I mean, it sounds kind of strange maybe, but let me show you some pictures to clarify this. Again, you may read like it's full of mathematics, and none of this mathematics is controversial. It's all like regular theories. What Kyriakos does, like all of these equations, they're like really, really accepted stuff. There's nothing he invents, actually. Like you can see there's how many references there are. He just tries to give a physical meaning to these expressions, which are meaningless most of the time. In regular, let's say, quantum field theory, okay? Meaningless in the sense that they describe objects which are completely abstract, you know, removed from reality, lacking ontology, if you wish, all right? And again, as we've already noticed, that was his objective, according to his own words, is to, you know, bring back ontology into these lifeless, abstract equations, all right? So let us see. Let us see some pictures so you would understand what well, the author, I guess, meant. So here we have like a regular photon. According to him, it's limited. Like this is the whole photon, okay? It's one oscillation of electric field and magnetic field transfers to it, okay? And it's flying somewhere there. And we say, well, what if we drag it here along this end and kind of connect it back here, so make a loop out of it, okay? That's the idea. That's the transformation that produces massive particles out of this linear massless wave. So the part A represents a linear photon. That's a completely regular normal photon, okay? That obeys the linear wave equation. And by linear, we mean here what people usually mean in physics. That means there's no self-action of the field, so to speak, okay? So this photon can just, propagate freely with no interference, like no distortions, basically. Like it can travel forever just in this form, okay? And then if you twirl it like this, if we connect this end to this end and make a loop out of it, you get something like this, where half of the circle you have, for example, electric field outwards and then half inwards, and magnetic field half downwards and half upwards. So you get this weird structure, okay? This is what he calls the intermediate photon. So this is a massive particle already. Why is it a massive? Well, you have to look into Maxwell's equations, like how exactly they transform. But you get also imaginary unit from it, because there's a tangential current here, actually. And you also get a mass from this, because, again, electromagnetic field, if it's sort of enclosed in a limited volume, it will have mass, you know? I mean, it has been known for more than 100 years as well. The so-called electromagnetic mass, or if you wish, Einstein's E equals mc squared type of formula, okay? So some mass would be present. But this thing is unstable. However, I think Kyriakos, like, I needed to refresh actually my knowledge of his theory, but I think he says that this is kind of the Z boson. So kind of this massive weak boson, but it doesn't really matter. He also calls it like something like Z boson, you know, it's some analog of a Z boson basically. And he also, I think, in some places he actually predicts that if this is true, then Z boson should have electric dipole moment, because you can see that the electric field is kind of directed like this, all right? But anyways, this structure is also unstable, and it will fall apart into like what he calls where wait, where are these words? Well, intermediate photon breaking, that this is this process. Well, basically it disintegrates into two halves, where one half has electric field inward and magnetic upward. I mean, all these directions are pretty much arbitrary, and the tangential current goes this way, and the other half is with electric field. Actually, I should have zoomed right away. The electric field outwards and the magnetic field downwards, and the tangential current goes this way. I mean, the directions are arbitrary, obviously. I mean, we can put the axes wherever we want, basically. But these two things correspond to so-called retarded and advanced electromagnetic waves in this field configuration, okay? So this is kind of the physical reason. Now, in terms of equations, you may say that intermediate photon, this structure, is described, again, I'm not going to show you all of this, like you can look into it if you wish. This is described by klein-gordon equation, this boson, and this stuff is described by Dirac equation. So it is known that you can decompose Klein-Gordon's equation into two Dirac equations. As you may have guessed, these structures correspond to electron and positron, all right? Because they have everything opposite, basically. Okay, so these are the antiparticles. So this is how you get the pair production, essentially. And I think he calculates the lifetime of this structure. I mean, it is known that a photon can produce electrons and positrons if it has enough energy, right? But why don't we see, at least in air quotes, this intermediate structure? Well, his answer is that it lives very short. He has a calculation somewhere here. I think it's something like 10 to the minus 26 seconds or something. So it basically is destroyed almost immediately. Oh my God, there's so much stuff. Actually, I highly recommend you to read it. Like, the purpose of this video is just to show you the ontology, the physics behind the equations. All right. Let me just stop here. Let me just say that according to his calculation, this structure is very short-lived. Therefore, we don't observe it. What we do observe is photon turning into electron-positron pair. And how can you twirl this photon into this loop is a good question, actually. But here you need some nonlinear physics again. You need some sort of nonlinear electromagnetism, for example, the one that would be achieved around these conditions, right? When the electric field would be pretty strong. And actually, if you think about it, I mean, what we see is, for example, pair production in the field of atomic nucleus, right? And how close do you have to go to the nucleus to get fields like this one? It's actually a sort of a napkin type of calculation that any 10th grade student, at least in my country, can do. It's something like 10 to the minus 14 meters, okay? So that would be like an order of magnitude bigger than the size of the nucleus itself, all right? So roughly speaking, 10 or maybe 20 nuclear sizes is where you'll get fields strong enough to do stuff like this. So you will have, for example, this is kind of all my conjecture. I don't think Kyriakos talks about this, but I've been thinking about this, and that these are my thoughts. So we have a nucleus, okay, positively charged. So it has a pretty strong electric field if you get close to it. And if you have a photon which has a size, I'll just denote it with this line, like it has fixed length, basically, right? So when it is approaching this field, which is spherically symmetric, for the sake of this argument anyway, so some parts of it are already in this field and are already feeling these nonlinear effects. So for them, effectively, there will be some refractive index because of this, stronger field. Because stronger field actually influence the refractive index, even if in a vacuum, if we're talking about these types of fields. So, I mean, in modern quantum field theory, they would tell you that even in a vacuum, these virtual photons will create electron-positron pairs, essentially, which would influence the motion of this photon. Maybe not even electron-positron, also muon anti-muon, or tau anti-tau, or whatever else, okay? So what will happen is this guy is getting, closer and closer to the nucleus, so the refractive index is bigger and bigger, so it will start twirling like this. Actually, doing it in the same color is a bad idea. It will start twirling like this. And at some field intensities, it's not at all crazy to assume that it can, by the time this end of a photon enters this field, it will be twirled completely. And that's how you'll get this intermediate boson. And then, according to Kyriakos, it would fall apart and form electron and positron, right? So that's the idea. At least that's the... My God, that doesn't even look like a circle. Anyway, so this is at least phenomenologically an idea of how you can get this process to happen, okay? So hopefully it makes some sense. And if you read the analysis, if you look into equations, especially if you know what we're talking about here, if you're into this whole quantum field theory / local gauge invariance principle, you'll see how much sense it makes. All right. Just one comment of this sort I'll make for like maybe more general public. Okay. We have again this mysterious thing called a wave function, which has components without any physical meaning, except if you treat it through, again, Born's rule, where wave function is the amplitude of the probability of finding a particle in a certain state. But according to Kyriakos, like if you look, again, we've started from this postulate number 1, which is basically Maxwell's equations, all right? So according to him, for example, in Dirac equation, what do you have? You have actually the wave function. But in this theory, we only have fields, the magnetic one and the electric one. And the thing is, then you can reinterpret Dirac equation as an equation for the electric and magnetic fields. You can see we obtain the electromagnetic form of Dirac equations. So finally, what was called the wave function gains some physical meaning, okay? It's just electric and magnetic fields, you know, kind of stacked into a single entity, all right? And it makes so much sense. It's kind of crazy, actually, no? All right. But again, you can read all of this analysis. It's very good. I'm just like, I don't want to make this video again an hour long or 2 hours long. This book is very easy to read, again, if you skip the mathematics. The mathematics is just actually not so much needed, if you ask me. Like it's just the same thing formulated in different symbols, essentially. Okay, so we've looked into electron. You may ask, well, what about the other particles? For example, neutrino. Well, as you may know, we not only have linearly polarized electromagnetic waves, just like these, right? Where we have electric field like here and there, magnetic field here and there. We can also have circularly polarized waves, like this, where the electric field is kind of like corkscrewing around, and the magnetic field is kind of corkscrewing around perpendicular to it. So you can even represent a plane wave that is a regular photon as a vector combination of two such waves rotating in the opposite directions. So if you now twirl this structure, connect the end to the beginning, you get a neutrino and antineutrino. So it will have additional quantity called, well, basically something like helicity, right? We'll have chirality. I think chirality is what people usually use. So this corkscrewedness, okay? So that, let me show you another picture like this. This is not very helpful, I think. Well, maybe a little bit, but this one is what I really like. So you have some sort of a Möbius strip, where if you start with, let's say, electric field vector like this one, then it's corkscrewing around, and in one full rotation it becomes opposite to itself on the previous phase, right? So that's how you get chirality of neutrinos and antineutrinos. But fundamentally, it's the same thing. It's the same thing as electron, just, you know, corkscrewed around. And that's how you don't get electric charge, because your electric field is half of the time it's outwards, half of the time it's inwards. And plus it's a fermion, because again, it's only like 1/2 of the whole thing. You have to rotate it again for the electric field to become outwards again, you know? So it makes so much sense. I'm telling you, it's kind of crazy. Yeah. And here, by the way, I didn't talk about charge a whole lot, but you can see, for example, for the electron and positron, like if the electric field is inwards, this means we're dealing with electron, right, technically. And if electric field is outwards, this is a positron. So yeah, so this structure, even though there's nothing in the center of it, right, there's effectively a field lines outwards, which means that like virtually in the center of it, there's a positive charge. And here virtually there's a negative charge inside. So the charge is like an integral characteristic of this big structure. Well, by big, I don't mean it's actually big. I mean it's distributed in space. It has some size. Once again, another good property of Kyriakos' theory is that he actually has size to things, okay? He actually has structure to things. And again, when we're talking about like what is spin, what is blah, 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 like this is the answer, you know? How can a point-like particle have a spin? It cannot. Like, it's just a stupid idea, which is again promoted through regular quantum mechanics and quantum field theory. But here we don't have point-like particles. We actually have some structures. And it's very understandable how they can have spin, energy, mass, blah, 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 charge, okay? Yeah, so we talked about neutrinos. I actually have in my notes another page. I wonder what that is. Oh, it's actually, I've already shown you. Okay, so what about the other particles like hadrons? I've promised you hadrons, all right? Something like a proton, for example. Well, here, again, you have to consider a more complex form, basically, of essentially Maxwell's equations, which would be called Yang-Mills equations, okay? So this is kind of a, well, very roughly speaking, okay, it's a nonlinear analog of Maxwell's equations. So when we're dealing with something like this, okay, when the vacuum of electromagnetism itself starts interacting with even the linear waves, so to speak, with even the photons of a regular sort, okay? So in this case, what we're dealing with, again, other style of equations, so things become much more difficult. However, you can still sort of try to linearize them. Because if you think about this, like the Lie algebra that quantum field theory uses, it's linear. It's actually a linear approximation of some actual nonlinear field. Even in Yang-Mills theory, even in local gauge invariance principle, you're still dealing with linearizations, okay? So yeah, so this theory is like absolutely the same in terms of generality, just as the standard model / quantum chromodynamics in this case, okay, when we're talking about the physics of hadrons. So, well, there's so much to talk about, but for example, we'll have also many currents, many fields. What are quarks? We're going to talk about in a minute. But since we have a closed system, that is, for example, a proton, okay, at least one of the currents can be expressed through others, even though he actually says it can be assumed. So maybe he's wrong in this case. I don't know. Like, I don't think he did this to the end. Still, in this case, there are only 8 different terms of interaction. What are 8? What is the number 8? Why is it significant? Well, because there's 8 type of gluons, okay? So even the number of gluons is explained in this model, even though I haven't given you the model itself yet. I've just told you that the equations are more complex, okay? But the model itself, at least the linear form, is, in his idea, is such, is like a trefoil knot, okay? So here we have like, it's not a very good depiction. This is a much better depiction. So if you twirl a photon into this, it has no self-crossing, by the way, but it's quite a complicated structure, okay? I mean, at least to me, maybe you have a very good dimensional perception. Like, it's pretty hard for me to understand this structure, but it's a very well-known structure. It's called a trefoil knot, okay? And the beauty of it is that the trefoil knot is actually the simplest example of a non-trivial knot. So it would make sense if for example, protons as like the super stable particle that we know about is also the simplest, okay? And what does it mean non-trivial? It means non-circular. So generally, you have a knot which is just a circle, which is also very simple, okay? Even simpler than a trefoil one. So this knot is represented in Kyriakos' theory. Again, it's a linearization of the theory, okay? It's a linear representation of an actual, more complex theory, which we have no idea about because we can't deal with crap like this, okay? Still, in this linear approximation, we have circles which are represented by neutrinos, electrons, and positrons, possibly other leptons as well, but we'll leave them for now. And we have simple baryons like proton, represented by the next knot possible. So you can twirl a photon like this, you'll get neutrinos or electrons or positrons, or you can twirl it like this, then you'll get protons, and possibly neutrons, by the way. Maybe these others, more complex knots, represent some others. Like, for example, we like supposedly, again, they found a so-called tetraquark, a particle composed of 4 quarks. So that would be this structure, I assume at least. I don't think Kyriakos actually talks about this, but maybe, I don't know. Then they found a pentaquark. It would be something like this, all right? Etc. Maybe. I don't know, actually. But for baryons, he proposes this sort of structure. Again, a linear structure, okay? So in reality, probably more complex, but this is the linearization. And what is good about it is that it is handed as well. So there's a right knot and a left knot, and they cannot be mirror imaged into one another, which means that it's gonna be a fermion, okay? So it's gonna be a semi-integer spin, just like a proton has, which is good, all right? And what are these 3 leaves? It's quarks. And that explains why you cannot get quarks out of the proton. It's because, well, you'll ruin the whole structure, okay? Like, this thing cannot exist on its own because it's like it's a part of the bigger thing, you know? And there you go. And there are 8 terms of interaction. There are 8 gluons in thick air quotes, you know? But fundamentally, it's electromagnetism. It's just a nonlinear electromagnetism of this sort. Okay? Nonlinear. It's when the vacuum itself starts impacting your behavior. And again, it's all very, like, not very alternative, let me put it this way, okay? Like, he never gives you any equation which wouldn't be, which would be unknown, let's put it this way, okay? In a good sense of the word. He just tries to explain where this stuff comes from in any sort of meaningful way. And I think this way that he has invented is so meaningful, it's kind of crazy that people don't, you know, acknowledge this. So this is why I'm doing this video, okay? So this is one possible picture that he actually, yeah. So well, it's not a good visualization. I mean, it's obviously some old program that he used. This is a good visualization, but imagine that this wasn't just some sort of like a wire or rope or whatever it is, but it was like a trajectory of the field change, right? Something like this. But it all has to like self-interact constantly with these so-called gluons, which are really just the terms of currents and fields, electromagnetic currents and fields. Yeah. Well, there you go. That's the picture of baryons. A much better one than the quark model, which has so much sense because, again, it explains, at least in air quotes, why we use local gauge invariance principle, which is, again, what is it about? It's about imaginary rotations of imaginary objects in imaginary space. Here we have real objects, or at least linear representations thereof, in real space. We have a real meaning of wave function, that is the electromagnetic fields themselves, the electric and magnetic, okay? We have explanation of why spin is such as it is. We have explanation of what, for example, neutrinos' chirality is, etc., 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 etc. Like, that's it. That's it, I would say. So here he actually draws some conclusions himself. So the fractional charge of quarks, like we've talked about this, right? That the charge is an integral characteristic. So you just have to look at where the fields are directed, right? So these separate leaves, separate like loops, will have a fractional charge perhaps. Like for example, you can see that even in this like simplified depiction, parametric equation for the trefoil knot, you have two separate frequencies, right? There is T2T, T2T, and here's 3T, okay? So there has to be two similar quarks, let's put it this way, and one different quark, so to speak. And this is what you have in both proton and a neutron, actually, like UUD or UDD, right? So that's speaking of mass. And what else? What else do we have? Like confinement, we've already discussed this. So the mass of the hadron is not only the sum of the masses of these separate, pieces of the whole loop, but also their interactions. Okay, understandable. Spin. This is the point I just made actually. It's nonlinear. Gluons, these interactive terms, are obviously also not observed without the whole structure, right? Because it's the interaction of the structure with itself in the first place. The color of quarks, according to Kyriakos, can be identified with the quark currents. So that would be the currents in these separate, parts of the bigger loop, okay? Well, etc. All right? Hopefully, I was able to demonstrate to you that this is a really great model. Again, I'll give all the links. You can read the whole book. And by the way, not only this book, he also has a really good book on Lorentz invariant theory of gravitation. So in case you're interested in, let's say, a relativity theory without Riemannian space, that is like a full Minkowski space reformulation of gravitation theory. There was actually another scientist in Russia, I think his last name was Lagunov. It could have been Loginov. These are very similar last names, so I tend to confuse them often. Who also had the similar theory. But again, it's actually like both of these books, I have to say, both this one about the particles and this one about the gravitation, they actually are good, even like just textbooks. Because again, he gives all the references, he gives all the equations just as they are. His objective is to try to make sense of these equations, of what the people thought, what people wrote about them, etc., etc. Okay? So bring physics back into physics, as sad as it sounds, all right? Yeah. Well, hopefully that would be enough.
Well, as you can see, the model of Kyriakos gives a reasonable, let's say, ontological, let's say, picture of what elementary particles is. Particles such as electron, neutron, electron, neutrino, and actually also perhaps neutron and proton, that is hadrons, and perhaps other hadrons as well, such as in fact baryons. The particles which are supposedly, according to quark model, are made of 3 quarks, but here they are more like, trefoil knots or something like to that effect. I have to say that Kyriakos himself has considered this to be just a linearization, so that's like a first order approximation of the real thing, where the real thing would be something much more complex, which would be, let's say, described or at least produced by some nonlinear fields, some nonlinear quasi-electromagnetic or maybe actually electromagnetic fields, but we can't really work with this unless, you can only like asymptotically approach it. So this would be the model that I've shown you here would be the first approximation, all right? Of course, there are still many issues with it, but at least I think it shows, it gives like a physical, ground to where things like Dirac equation, for example, are where they appear from, essentially. Okay, so it gives a reasonable explanation to this, and it also gives a reasonable explanation why these imaginary rotations of imaginary objects in imaginary space can actually describe the behavior of elementary particles and the statistics of the particles themselves, because they actually represent the actual rotations of actual structures in actual space. All right, so in some sense, it also explains, at least in air quotes, the so-called local gauge invariance principle, which is again absolutely inexplicable in, you know, vanilla quantum field theory. All right. Okay, so hopefully this was fruitful for you. I gotta tell you that pretty soon, like maybe 2 or 3 videos from now, I'll make a video about another phenomenological model of elementary particles, developed by a Russian physicist Burtaev. But again, this will be like in 3 videos from here. So that's also a very interesting model, even though there is no model in this sense, in the sense that you've just seen with Kyriakos' model. So Burtaev has only like a phenomenological approach. So he, like a very, very crude, like, you know, we say that electron is made from parts which have these properties, but how exactly they look, how they behave, we don't really know, you know. It's this type of model, a phenomenology, as Burtaev himself calls it. But that will be another video for another day. Thank you for watching. The eons are closing. If you wish to support me, please consider joining my Patreon. That is patreon.com/philosopher. See the link in the description. Or if you have a scientific theory of your own and you'd like my help in developing it, please join my alternative science coaching program, also available through Patreon.